In this video, we're going to do another example of integration by parts. This example is going to be a little special integration by parts example because we're going to see that if we do integration by parts enough times, spoiler twice, the original integral is going to pop out again at us. It's going to make an appearance at us after doing integration by parts twice. This is what I like to call a cyclical integration by parts problem. They usually have a flavor of some exponential times either a sine, like in this case, or something like a cosine of some 3x or something like that as well. But these are what I call these cyclical type problems. We're going to do integration by parts twice. We're going to see the original integral pop back up, do some algebra, and out pops our antiderivative. So let's begin. So why integration by parts on this problem? Why not u sub? Well, remember for u sub, we might have the product of two functions just like we have here, but if we look closely at these functions, neither function nor a part of the function's derivative looks like the other thing there. So if we tried u sub, nothing's going to cancel out through that substitution. So we're kind of stuck at the u sub front, which is why we're moving into integration by parts. Again, we see we have the product of two functions in that integrand, and we can try applying the integration by parts formula. And for integration by parts, we differentiate one thing and we integrate the other thing. For this particular example with these cyclical type problems of an exponential times a sine, exponential times a cosine type situation, it's not actually going to matter what we call u or what we call dv. So I'm just going to arbitrarily pick one, and for our sake here, let's just say we want to call u is equal to sine of x. And remember, whenever we're doing these integrals, we can always try something. If we get stuck, we can try something else. So I'm just going to arbitrarily choose, in this case, u is sine of x. When I differentiate it, we of course get cosine of x. So du in this case is cos of x times dx. Right? And that makes everything else in that integrand our dv portion, namely that exponential as well as that dx there. So dv is equal to e to the minus 2x times that dx. Remember, what we care about for integration by parts is getting v by itself. So we integrate both sides. When we take the antiderivative of that right-hand side, we will get a 1 over minus 2 e to the minus 2x. Because remember, if we hit that v now with a derivative, we want to get back to what's inside of that integrand. All right, so integration by parts for us, we have all of our characters, a u, du, dv, and v. We plug it into the integration by parts formula. And just for the sake of this problem, remember, whenever we do a step of integration by parts, it's always going to be equal to the original integral. So I'm just going to write down our formula, uv minus v du, with our original integral on that left-hand side. So let's just plug in those characters now. So plugging in u, we have that sine of x. Plugging in that v, we have the minus 1/2 e to the minus 2x. And now plugging in the v again into that integral, we have minus 1/2 e to the minus 2x. And then plugging in what we have for du, which is our cosine of x times dx. And that's still equal to the original integral that's on that left-hand side. So let's take a look at what we have now. Inside of this first step of integration by parts, we have two functions just being multiplied out in front. Again, those functions, they are what they are. There's no integral attached to it. So we set our sights on trying to integrate what's left over here. And if we look at this integral on the far right side, well, it doesn't look any more simple than the original integral. We still have an exponential times a cosine sitting there. It's not an antiderivative, we should know. So let's try doing integration by parts again. Before we do that, I'm just going to rewrite the previous line here. So we have that 1/2 e to the minus 2x times sine of x. And then minus a minus, again, because we have a minus outside that integral, minus inside the integral, that turns into a plus. I'll pull that 1/2 in front of that integral, and we get this as 1/2 integral e to the minus 2x times cosine of x. Again, that integral itself that we're left to do here, it looks very, very similar to the original one, just with a cosine now instead of that sine. But let's try applying integration by parts again. And just remember, when we integrate by parts again, we want to kind of keep the same characters as u, same characters as dv. What I mean by that is, previously, we let u equal that trig function, that sine of x. So in this case, when we define u for our second integration by parts, we're going to let u equal that cosine of x. We want to keep kind of doing the similar thing. If we did it the opposite way, we would actually just end up back at the original integral just by undoing that previous step. So we don't want to undo the previous step. So call u cosine. So when we differentiate that cosine, we'll get a minus sine. And then, of course, when we get du by itself, we get du is equal to minus sine of x times dx, which makes everything else under that integral our dv portion, that exponential and that dx again. So dv, once again, is e to the minus 2x dx. And again, we want v by itself, so we integrate both sides, and we get v, once again, is minus 1/2 e to the minus 2x. Okay, so we're going to do another step of integration by parts. Just so we're on the same page, this step, combined with the step we just did, is still going to be equal to the original thing. So this original integration by parts, we can actually, or this original integral, we can carry all the way down. So I'm going to keep doing that. So the original integral on the far left side, integral e to the minus 2x sine of x dx, that's going to be equal to the stuff we had from the previous integration by parts. Again, those two functions being multiplied out in front. So we have the minus 1/2 e to the minus 2x sine of x. And now we have the integration by parts formula we're going to plug into. But let's just be careful here, because in front of that integral, we had that factor of 1/2. So I want to throw this factor of plus 1/2 out in front. I'm going to draw some square brackets just so I don't lose anything. And I'm going to write our integration by parts formula inside of this. uv minus integral of v du. Just so when we plug in stuff, we don't lose any minus signs or anything like that. So I'll just keep writing what we have here. Far left, e to the minus 2x sine of x dx. That's equal to the product of those two functions, minus 1/2 e to the minus 2x sine of x. Again, that's from the first integration by parts. We have that plus 1/2. That coefficient that was in front of the integral that we just did that second integration by parts for. And now we're going to plug in all of those characters into this integration by parts formula. So the second time, our u was cosine, so that u, we will write a cosine of x. The v in this case was still equal to the same v that we had before, but it doesn't, so we'll just plug that in, or the v we just had up there, minus 1/2 e to the minus 2x, and minus the integral of v, which we just wrote, minus 1/2 e to the minus 2x, times du, which again, du now, is that minus sine of x dx. So let's just, before we do anything else, let's just do a little bit of sign simplification just so we don't lose any signs and stuff like that. So we still have on that left-hand side that same integral we started with of e to the minus 2x sine of x dx. The right-hand side, I'm going to leave those two functions that we're multiplying alone. And then I'm going to start distributing what we have left here. So we have this plus 1/2. However, we have this minus sign in there. So this will actually become a minus 1/2 times 1/2 from there. So we get a minus 1/4 times e to the minus 2x cosine of x this time. And now when we distribute this positive 1/2 into the next term, well, let's see all these negative signs that'll cancel out here. So let's zoom in for a second. So I'm just going to highlight these. We have one minus sign from outside the integral. We have a minus sign from that minus 1/2. And we have a minus sign from that minus sign of x. So two of these minus signs are going to cancel. Let's just say these two minus signs inside the integral, because two minuses getting multiplied give us a positive. So overall, the sign on this thing is still just going to be negative in front of that integral. And when we multiply a positive 1/2 by it, it's still going to be something negative. All right, so nice way to settle that. So let's distribute this 1/2. So this 1/2 out in front, when we multiply it in or substitute it in, it'll multiply this 1/2 there. So we'll get a plus 1/4. And then we have the integral of e to the minus 2x times sine of x still there. And woof, we just did two integration by parts. And if we look at what we have, well, we have the original integral is equal to this big string of things on the right-hand side that we kept getting new things from doing integration by parts a couple times. Now, look at this original integral. It's an integral of e to the minus x or minus 2x times sine of x. If we look closely at that last integral on the right-hand side, without that factor of 1/4, that's exactly the same integral. So this is what I mean by this is a problem where we did integration by parts twice, and the original integral popped up again. Now, this is something special about this type of case. We're going to treat this integral as like it's a variable and do some algebra with it. What I mean by that is what we care about is actually solving for that integral in terms of all the other stuff that's there. So let's subtract from both sides minus 1/4 that integral on the right-hand side. Again, the integrands are the same. So when we subtract these things, we really just have to subtract and do some arithmetic with their coefficients. So this coefficient in front of the integral on the left-hand side is a 1. So if we have that integral minus 1/4 of the same integral, well, overall, that's going to give us, on the left-hand side, 3/4 of that integral. On the right-hand side, well, if we have 1/4 times that integral minus 1/4 times that integral, those two things, well, they just cancel out, just like doing some standard algebra. So on the right-hand side, we have left is a minus 1/2 e to the minus 2x sine of x minus 1/4 e to the minus 2x cosine of x. And what we care about again is what that integral is equal to. So if we want to get this integral just by itself on the left-hand side, the next step we do is basically just divide both sides by 3/4 or multiply both sides by 4/3. So if we do that, we see, well, multiplying both sides by 4/3, those coefficients on the left-hand side cancel, and we just get that integral by itself. On the right-hand side, well, we actually just have some functions. 4/3 times minus 1/2 e to the minus 2x sine of x minus 1/4 e to the minus 2x cosine of x. And at this point, you might be saying, well, so what? But if we take a step back for a moment, remember what we care about is what this integral is equal to. On the right-hand side, we found just some functions. There's no integrals on the right-hand side. So we actually just found what that integral on the left-hand side is equal to. It's equal to that the collection of functions on the right-hand side. The only thing that's left to do is add a plus c. And the last thing I just want to mention here, was I think this is a very slick way that we're able to get this integral through a couple integration by parts where the original integral popped up again, so we could do some algebra to get that integral by itself, to set it equal to whatever we did through that integration by parts stuff. For whatever reason, I really enjoy these types of integrals. But to take us back to the beginning, remember, we arbitrarily chose, or I arbitrarily chose, let's call u equals sine of x here. And dv was that exponential stuff. For these types of integrals, where we have things like an integral of e, let's just say to the ax times sine of bx dx, or an integral like e to the ax times cosine of bx, it actually doesn't matter what we call u and what we call dv, as long as we're consistent throughout. Both of these types of integrals will be cyclical. We'll do integration by parts twice. Original integral will pop back. We do some algebra, and boom, we have our antiderivative.